Now, what I'm saying is, what if the growth function of some algorithm is log n? Here we are assuming the growth function is exactly log n, okay, for this table. What I mean by that is a function, we can have a function 2 log n that will still be big O of log n. I can have a function 5n squared that will still be big O of n squared, okay? In this table, I'm just assuming that this function here, which is big O of log n, is actually exactly f of n equals log n, okay? Just for the sake of this example. Okay, so when n is 10, and then I'm computing what is the log n of 10, I find the log n of 10, and then I multiply it by, I'm saying basically that I'm assuming each of these algorithms, they execute on a processor which is 1 gigahertz. In the next slide, I show you how to compute each value. I'm showing you an example which shows you how to compute the values in the table so that you know where these numbers are coming from, okay? But this is not really the meat. This is not really what we want to discuss, okay? We don't want to discuss how we derive the numbers, but we want to observe what's happening. So for a logarithmic algorithm, or logarithmic growth algorithm, which is the first one, when n is 10, we have 3 microseconds. The algorithm takes 3 microseconds to solve. Okay, when n is a billion, it takes 30 microseconds. So n changed from 10 to a billion, but the execution time changed from 3 to 30, just 10 times. The input changed 100 million times, or several orders of magnitude, and the logarithmic algorithm increased only 10 times in terms of execution time. Now, what about the linear? It starts at 1 microsecond when n is smallest, and it grows to 1 second. So that makes it grow how many times? Times? $100 million, right? Are you still with me, or are you completely switched off now? I'm saying that here, when n was 10, the execution time was 0.01 microsecond, which is 10 nanoseconds. And then when the input is a billion, it becomes 1 second. Now 1 second is a million microseconds. So million times 100, that's 100 million. Now when the algorithm is log linear, it starts at 33 microseconds and it finishes at half a minute. When the algorithm is quadratic, it starts at 0.1 microsecond and it finishes at 31 years. When the algorithm is exponential, it starts at 1 microsecond, and when n is just 100, it takes 4 times 10 to the 13 years. Okay, and when n is factorial, and if n is 30, it's gonna take that number of years on a computer which runs at speed 1 gigahertz, like your smartphone. Okay, so this table just to show you the relationship between the asymptotic complexity that we do, and if we try to apply the results, or imagine applying the results on some hypothetical machine, in this case that runs on 1 gigahertz. Okay, so that you know that as the complexity increases, the time to solve the problem increases. Okay. Now we will see like a more realistic example. We are going to assume that we have an algorithm which is big O of n squared, and another one which is big O of n log n, log linear, and they solve the same problem. I mean, we have seen examples of that. We have seen the algorithm that sums up the numbers from 1 to n, and we said this algorithm is we have seen two versions. We have seen a constant growth version and a linear growth version, correct? Right. Okay, so constant growth and a linear growth. And in this case, we are assuming we have two algorithms, one which is quadratic and one which is log linear. And we are going to execute them on two different machines. So the one which is quadratic, we are going to execute it on a supercomputer, which basically can execute that many instructions per second. And on a smartphone, which can execute that many instructions per second. So the big O of n squared algorithm, we are going to execute it here, and we are going to execute the big O of n log n here. Now, why do we want to do that? Because some people might think that computers nowadays are very fast, and there is no point really in trying to make algorithms efficient. Okay? If you have a very fast computer, you might think, well, what's really the point of trying to look at the algorithm and if it's efficient or it's not? We will see that if an algorithm is not efficient, even if we put it on the fastest computer in the world, it's going to suck. And if an algorithm is efficient, if we put it on a smartphone that you buy from off the shelf, it is going to be efficient. So efficiency, writing efficient programs, has nothing to do with hardware. Okay? No matter how fast hardware it is, if the algorithm is slow, is not efficient, it's going to cause you problems. So that's the fastest computer in the world. Obviously, it's distributed and has lots of things in it. And that's a smartphone. So what we're doing here, so when the input size is 1,000,000, the supercomputer takes 61 microseconds to solve the big O of n squared algorithm, but the smartphone takes 70 milliseconds. So even though the algorithm here is less efficient than this one is being faster. The supercomputer is being faster. And that's only, even though the algorithm here is less efficient than this one is being faster. The supercomputer is being faster. And that's only because the input is still not that big. Now, if the input increased to 1 billion, now the supercomputer takes twice as much. It takes 1 minute, but the smartphone takes just less than half a minute. When the input is 1 trillion, this takes 2 years, and this one takes 9 hours. Okay? So that's a supercomputer, which is 13.6 million times faster than the smartphone. So when the smartphone executes one instruction, that can execute 13.6 million instructions. So it's that fast. But because it's running a non-efficient algorithm, and the smartphone is running an efficient algorithm of the same problem, of course, we only compare algorithms of the same problem, that solve the same problem. I mean, as you can see, when the input starts increasing, the efficiency starts dropping considerably of the supercomputer, and the smartphone is coping fine a little bit, because n log n is still is not like a very efficient algorithm. And it's not fast anyway. I mean, 1 gigahertz, it's not really fast, especially for inputs of size 10 to the 12. Okay, so this is like just a lesson to know that if you have the fastest computer in the world and the algorithm is not efficient. I mean, remember, if you look at the table, n square. N square, oh my god, n square and n log n are actually close to each other. Okay, we did not give an exponential algorithm to the supercomputer and the logarithmic algorithm to the smartphone. That would be unfair. Okay, we have picked two algorithms which are adjacent to each other in the table. One went for computer and one supercomputer, and one went for a smartphone and supercomputer. Okay, So this is just to say that the algorithms are not that far away in terms of complexity, but still, as you can see, the difference, huge difference in efficiency. So these are just rules of thumb. I mean, we call them rules of thumb because they depend on certain things, on the context. But usually, exponential algorithms, you cannot really use them that much. If you have a small input, yes. Otherwise, I mean, there is no point. Quadratic algorithms, you can use them up to a few millions. Log linear, up to a few billions. Linear algorithm, perhaps up to few trillions. This is like assuming you're not using your calculator or your smartphone. I mean, assuming a desktop computer like 4 gigahertz, nowadays computers. Logarithmic algorithms are the best, okay, but it's very hard to derive them, and sometimes you cannot derive a logarithmic algorithm. By the way, it's not always possible to have an efficient algorithm. Sometimes the problem is very hard. You just cannot find an efficient algorithm. But usually by thinking harder, you try to optimize the algorithms you have. We will see examples of that when we do sorting later on. So these are rules of thumb. Okay, they're not like engraved in stone. They are just rules of thumb for you to know how to discuss things. If you have a decent PC, then these kind of things apply. Okay, a note on logarithms. Sometimes in this course we need to talk about logarithm. The logarithm we use are logarithm of base 2. Okay, I just make a silly remark. There is algorithm and there is a logarithm. Okay, they're not the same. So there is log 2. So we will use log 2 because we are binary people, or we are computer scientists, and we use binary system. So when we say logarithm, we are talking about logarithm of base 2. Normal people, non-computer scientists, they usually use logarithm of base 10. Okay. Sometimes when we give examples, I say, let's assume that the input is 1 million. And then I tell you, so if the algorithm is and then I tell you, so if the algorithm is if the algorithm is, stop being lazy and use the new paper. Okay. Sometimes I tell you, okay, n is 10 to the 6, and I tell you that the growth function f of n equals log n. And I ask you, so what is f of 10 to the 6? Okay. So that's log 2 of 10 to the 6, okay? Now, instead of using a calculator and wasting time, 10 to the 6 is 1 million in the decimal system. Now, 1 million in the decimal system becomes 2 to the 20 in the binary system. Okay. Now, why is that? It's quite simple. You know that the kilo is 10 to the 3, which is 1,000. That's in the decimal system. The kilo in binary is 2 to the 10, which is that number, right? That's in the binary system. So 10 to the 6 is really 10 to the 3 to the power of 2. Okay? Which is just almost the same as 2 to the 10 to the power of 2, which is 2 to the 20. So these are just helpful. These are things that help us do some mental calculation. Okay, so 10 to the 3 2 to the 10, 10 to the 6, 2 to the 20, 10 to the 9, 2 to the 30. Now why is it useful to change to 2 to the 30? Because log 2 of, let me go back, because log 2 of 2 to the 30 is just 30. Log 2 of 2 to the 30 is just 30. I mean, you know that if you have log of base a of some number a to the power of x, this log a and this base here, they just cancel out, and you just get x. That's just from logarithm rules. Okay, so log 2 of 2 to the 30, they just cancel out, and you just get 30. So in order to compute log 10 to the 6, you know it's log 2, so you just make it look like log 2 of 2 to the 20, and then this goes with that, and it's equal 20, without using any calculator. Actually, that's going to be more like 19 point, but we don't care. Okay, so 20 here, 19.9, 30, 29.9, 10, 9.9. So that's just a way for you to compute. When we give examples during the lecture, when I say 30, 20, you know what I'm talking about. Just a trick to compute logarithms very quickly. Okay, so far what do we know? We know algorithms. We know what they are. We know what it means for an algorithm to be efficient. It has to solve the problem in a time that we say it's manageable. We know that an algorithm has a growth function. We know that how to compare growth function together. And if a growth function is slower than another growth function, then its algorithm is better or more efficient than the other algorithm. And we know how to compare growth function with each other using the 5 operators: big O, little o, big omega, little omega, and big theta. So we already know that. The only thing which is missing now is how do we derive a growth function of an algorithm. So far we have looked, I mean, we did not have real rules to use it. We have seen the two algorithms that compute the sum 1 to n. One of them was constant and one of them was linear, and we just plotted them like that. We did not really define any rules. Now we will define the rules so that we can derive a growth function from any algorithm we see. Okay, so you know what sequential conditional loop statements are, and if you are in this course, you have already passed programming, or at least maybe advanced programming. So you know, if you see a piece of code, an algorithm is just a piece of code written in some human language, pseudo-human, pseudo-machine language. So if you look at the code, you understand, you can see this is a loop, this is a loop nest, this loop is inside this conditional is inside this loop. Okay, so we assume you know that. So the first step to do when we try to analyze an algorithm is to decompose the code into its components, loops, statements, etc., and then we apply these rules that you see in this slide. We will go through an example together, but we need to go through the rules first. So there is a rule for sequential statements. There is a rule for conditional statements. There is a rule for loop statements. So what is the rule of sequential statements? It says that I did not explain what's T of S. Okay, if we have statement S, then T of S is the number of runtime steps or the execution time of S. Okay, easy. S is a statement. T of S is the time to execute S, equivalently the number of runtime steps. So the number of steps of statements S1 and S2 executed sequentially is actually the number of that plus the number of that. I think that's pretty okay. For this I would need to use the projector. Okay, so we have some program which takes some input n, and then we have x plus plus in this program and y plus plus. So the number of runtime steps. So this is sequential. This is statement 1, and this is statement 2, and this statement are sequential, right? Sequential statements are statements that execute after each other. So these statements are sequential, right? Okay, so the number of steps of the two statements when they execute after each other is actually that plus that, right? This is what the rule is saying. If I have two statements executing after each other, then the total number of steps is basically the steps of the first and the second statement. Okay. Now, if we have a conditional statement written as if C, then S1, else S2, and if, then the execution or the number of steps is the number of or the time to evaluate the condition, plus we take the maximum time of either S1 or S2. Here's another program. Takes n as input. If some x is greater than 0, x y plus plus, else we have a for loop blah, which depends on n from 1 to n, z plus plus, and end. So in this case, we are saying that in order to, this is one statement, this is called the if statement, okay? So the number of steps here is the time to evaluate the condition, TC, and then we take the max of this part and this part. So this is T of, I refer to as S1, and this is as S1, and this is T of S2. Okay, T of S1 and T of S2, and we take the maximum. We have talked about this previously in the previous lecture. We said that we are interested in the worst case. When we have a program, we look at when the input is very large, okay, and also we look at inside the program where there are more steps, like inside conditionals. If you have a part which is one single statement and another part which unfolds to many statements at runtime, like a loop, then this is the one that we are interested in. Okay, so this is why we take the maximum, we take the largest one. So TC plus the maximum of either this or this, and in this case it's that. So in this case, TC plus T of S2. Right. And finally, we have the loop. Okay, so we have the loop. So it's the time to evaluate the condition plus the time to evaluate the body, okay, of the loop, multiplied by the number of times the loop executes, plus one final evaluation of the condition of the loop. Because the loop is going to evaluate, and it must evaluate one extra time at the end before exiting the loop. Okay. So if we want to give another example, so we have p of x so 4 let's use a while. For example, while k is less than or equal to n, do x plus plus. And let's say k starts at 1. Okay, so k, it starts at k equals x plus plus. And let's say k starts at 1. Okay, so k, it starts at k equals 1. And so it's going to check if 1 is less than or equal to 10. Is going to be less than or equal to 10, and then execute x plus plus, and then 2 less than or equal to 10, x plus plus, and until 10 less than or equal to 10, and x plus plus, and then it becomes there must be some k plus plus here as well, and then it becomes k equals 11. It checks here and it exits. So it's this condition evaluation n times, 10 times in this case, the body of the loop 10 times as well, and one extra condition. I usually will not penalize you if you don't include this, because it's just one extra step and it doesn't really affect the execution time that much. So the execution time of a loop is the time it evaluates the condition plus the time it evaluates the body multiplied by the number of iterations of the loop plus an extra evaluation for condition before the exit of the loop. Now, you will find tens of examples of this in previous examination with solutions, of course. So I suggest you have a look at them, so that, and if you have questions, you can email me or you can ask the TAs. Let's see this example now. Program P takes input n and does the following: a plus plus, b plus plus, for I in 1 to n, if c d plus plus, else for I in 1 to n e plus plus, and for and if. Right. Oh, can you read that? Okay. So a plus plus, b plus plus. I've used it alphabetically so that you can understand. So now the first thing is, when we do the complexity of that kind of thing, we said we are going to apply 3 rules: sequential statements, conditional. Going to apply 3 rules: sequential statements, conditional statements, and loop statements. Okay. So first we need to identify where these are. Okay. So we are going to look at the sequential statements. So okay. So this is sequential with this, which is also sequential with. I forgot and4, so these 3 statements are sequential at this level. That's a loop statement, and that's the body of the loop, okay? And these are the alternatives of the conditional statement. Now, what's the complexity of executing one statement? How much time it takes? Okay, yeah. So we say that this is big O of 1, okay? Because it's constant.
And the other one is big O.
And this one is big O of 1. And this one we still don't know because we need to look inside it. So the if statement has got big O of 1 here. The other part of the if statement is what? So this one is big of 1 here inside. And then the loop iterates n times. So it's big of 1, which repeats itself n times, and it becomes n times, not 10 times.
Big of n?
Yes. So the loop is big of n. This big of 1 is for inside it. Now we have a conditional statement. I did not mention what C is, but let's assume it's big of 1 as well. So it's big of 1. So the if statement has got this part here, which is big of 1, and this part here, which is big of n. So what is the complexity of the if statement?
1, 2, 3.
We said that the complexity is going to be the complexity of the condition plus the maximum of this and this. So what is the maximum of this and this?
2 plus n plus 2?
This one is big of 1,
Yeah.
and this part is big of n. Do we all agree it's big of n?
Yes. Yes.
So what is the maximum of big of 1 and big of n?
Big of n plus 1?
No, the maximum is not addition. The maximum, you have to choose one of them.
Big of n.
Okay, maximum, yeah. Maximum is not sum, is maximum. Big of n, so the maximum is big of n. And then we add big of n to the condition, right? So it becomes big of n plus big of 1, which is big of n plus 1. And this is what? We said that when we have a polynomial, we remove all the terms which are not going to affect the polynomial when n is very large, right? Right. It becomes big of n, right? And okay, so far we have found that the if statement is what? Is big of n. And then it is inside the loop, right? So it becomes what? So big of n, which is repeated n times. It's what?
Big of n. Big of n.
So we have n steps here. So for each step, we execute n steps. So it's n plus n plus n times, which is
Big of n. N power n. Big of n. Power n. The power n.
yeah, n squared. Okay, what we have is we have a for loop from 1 to n, right? And inside it we have an if statement which is big of n. So this in iteration 1 we have big of n. In iteration 2 we have big of n. Iteration n we have big of n. So this plus this plus this plus this is n times big of n, right? Which is big O of n squared. If that was multiplication, that would be big O of n to the n. But that's not multiplication. It's addition, because it's iteration after iteration after iteration. Okay, so big not multiplication. It's addition, because it's iteration after iteration after iteration. Okay, so big O of n squared. So we here, the loop now is big O of n squared. And the loop is sequential with... So it's big O of n squared plus big O of 1 plus big O of 1, right?
Yeah.
Okay, and this is what? Yeah, big O of n squared. So then the program is big O of n squared. So this program is quadratic. So this is how we do. We look at the program, we decompose it into a sequential, a loop statement, etc. And then we start combining this information. So big O of 1 plus big O of 1 becomes big O of 1. It's still constant. Big O of 1 plus big O of n is big O of n because it's bigger. Big O of n squared plus big O of n, it's big O of n squared. Maximum of big O of n or big O of 1 is big O of n. Maximum of n squared and n squared is n squared. You know, so it's very easy. You just need to combine them, and also you need to practice them. So there are lots of exercises from previous exams that will teach you or train you how to do these kind of things. So I suggest you have a look at them, and you can download them from the website. Right, are we done? No, we're not. We have still 6 minutes to wrap up. Huh? We finish at 11:30. Okay, so all that remains are a few examples that we have already covered the concept in this last example, and basically this is the wrap-up slide, which basically just summarizes what we need to do in order to find the asymptotic complexity, and that's it.